So exponential growth or decay follows this model. This is something you're going to have memorized for the test. This is the equation that you're going to model the data. So what modeling means is scientists or researchers gather data. You look at data and say, okay, this data has this kind of a trend. You fit an equation that describes that trend. If the trend seems to be exponential, you model it with this type of function. The amount at any given time t, that's what a of t means, is equal to a sub naught. That means the initial amount times the base of e raised to a power of k times t. That's a subscript of 0. Now, a, that's the future amount. A sub naught or a sub 0, that's an initial amount. T is an obvious one. What's t? Time.
Why can't it be a p?
For time?
No, for a of 0.
Do you notice some similarities between this and what we talked about last time?
The PERT thing?
All this is, you guys, is another form of PERT. That's all it is. Okay? There's no difference between these two. They're just different letters. But anyway, the K is what's referred to as a growth factor. It's really a percentage of growth based on the unit of measure of time. So if the measure of time is in years, then the growth factor is a percentage of growth per year. If the unit of measure in time is in days, then the growth factor is the growth percentage per day. So that's what a growth factor is. If the growth factor is positive, your substance grows. If the growth factor is negative, your substance decays. Because normally, with exponential functions, you guys, you don't need to really write this down, but normally, exponential growth functions have a base larger than 1, correct? Exponential decay functions have a base that's between 0 and 1. Wouldn't this be growth here and this be decay here? But with the model we're using, the base is always e. What's the approximate value of e? 2.7. So if the base is larger than 1, wouldn't this always be growth? And the answer is no, because if k is less than 0 or negative, that turns us into a decay problem. So that's how that works. We can use the same model to model exponential growth and exponential decay. You following? Got it. So the direction we're going to have to head, you're going to be given some data. You're going to be given maybe an initial amount. And after a certain period of time, you're going to be given an ending amount. What you're not going to be given is the growth factor, the percentage of increase on an annual basis or on a daily basis. You got to find that in order to make a correct model. Okay? Let's practice that. Example 1. Model exponential growth. Culture of bacteria has an initial count of 500 and doubles every 45 minutes. Little teeny thing. I don't know. Your task is to find a model that gives the amount of bacteria at any given time. we're going to have to in order to find our model. Now, here's why we need to have a model. If all we had was this information, a culture bacteria has an initial count of 500 and it doubles every 45 minutes, couldn't we find some future value? But the only future values we could find are intervals of 45 minutes. We could say, okay, we start with 500. After the first 45 minutes, how much is there? 1,000. After the next 45 minutes, there is, it doubles again, so there'd be, come on, simple math people, 2,000. But that's only increments of 45 minutes. What if somebody said, well, I don't want to know how many bacteria there are going to be after 3 days? Okay. You need to have a model so you can plug in just any value of t into the model to find a future count. So the model is going to look like this. A of t is equal to a sub naught times e to the kt. What do we know? What don't we know? We know the initial count. A sub 0 is equal to 500. And I'm glad you said that. This phrase right here, it doubles every 45 minutes, isn't our growth factor. That just says every 45 minutes it doubles. The growth factor is a percentage of change per unit of measure of time. So it's not, does that make sense? So it's not necessarily our growth. Essentially, yeah. Now, in order to solve for k, are you guys listening carefully? Because this is exactly how you're going to do that on your test. In order to solve for k, we can leave it as just an unknown variable, correct? But in an equation, in order to solve for a unique solution, there can only be one unknown in that equation. So if all we did was plugged in 500, because that's the only thing we know right now. If all we did was plugged in 500, is that enough information to solve for k? No. We need to figure out a way to substitute some other known values and leave k as the only unknown in order to solve for it. We know one particular time value of 45 minutes. So if we let t for right now equal 45 minutes, then what's the future amount at that 45 minutes? 1,000. So at time equal to 45 minutes, then we have this, 1,000 is equal to 500 times e to the k times 45. Now we've made an equation with only one unknown. Where did the 1,000 come from? It doubles because we've allowed 45 minutes to pass. And according to our information, after 45 minutes, the initial count doubles. Does everyone understand the direction we're heading here? What is it we're trying to solve for? We're trying to solve for k, the growth factor. Once we know the growth factor, we can substitute it back in and have our final model. Yeah?
For AT, the thing on the left is the time. Why do we not, like, select 245
The a sub t, that's just function notation. A of t means the amount at a certain time t. So what's the amount at our time of t at 45 minutes? It's 1,000. That's what that means. Does that make sense?
Okay.
Yeah.
Do you have to do 2,000 or could you do like 2,000 and 4,000?
You could, but if you wanted 5,000 to grow to 2,000, you'd have to have two 45-minute time intervals pass. You'd have to have an hour and a half. Does that make sense? We've only let one 45-minute pass, so that means it becomes 1,000. So if you divide by 500, then that becomes 2 is equal to e to the k times 45. Now we do natural log. Very good. Natural log of 2, or natural log on both sides. So that cancels the base of e. So what we have is the natural log of 2 is equal to k times 45. It's no longer an exponent because the base is gone. It's just a normal expression. What is it we're solving for? K. K is being multiplied by 45, so now divide by it. So k is equal to the natural log of 2 over 45. Now normally you would turn this into a decimal. Does anybody happen to have a calculator out real quick? I know they're not allowed, but I'm just curious what this is. Natural log of 2 over 45. 0.015. So what percentage of growth is that? It's about 1.5. Okay. So instead of estimating it, you just leave it like this, natural log of 2 over 45. Now, you don't stop here. The question didn't ask what's the relative growth factor. The question asked what is the model. The model's the equation. We were almost done at this step here. We just didn't know K. Now that we know K, we finish our model. The amount at any given time t is equal to the initial count of 500 times e to the natural log of 2 over 45 times t. Yeah.
If it's an interval, would it be natural log of 3 and 45?
Yeah, it would. Yeah, was there a question back there, Brady? Yeah, I saw your hand raised. No questions? Now, I know you guys listening, it's one thing to be able to do this, but do you understand what it is that we've done? What is the purpose of this model right here? You could plug in for any given time t, but you do have to be careful. What is our relative growth factor in terms of, and I'm talking about a unit of measure of time, what is it in terms of? Minutes. So if somebody asks, well, how much bacteria is there going to be after 3 days? Are you going to plug in t equals 3? You guys listening carefully? Because our relative growth factor is in terms of minutes. You'd have to figure out how many minutes there are in 3 days and then plug that in. Right? Okay. But that's really how this math is useful. People make observations, they gather data, they find trends. But in order to make predictions based on that trend, you have to have an equation. That's called modeling. That's a really powerful skill to have as a mathematician, being able to model data to be able to make future predictions. It's not always easy, it takes practice, but it is extremely useful. Let's try it again. Example 2. Ooh, these are all good. Try to do this one. See how far you guys can get on this one. This one's slightly more complicated, actually. We better do this one together. What's the one thing that we don't have in this one that we had on the last one? The initial count. And we still don't have the relative growth rate or the growth factor. We have actually two pieces of information. We know that after 2 hours there's 400. After 6 hours there's 25,600. Yeah.
We just like pretend that 400 was the initial amount and 4 hours later.
That's a great suggestion. That's a great suggestion. The more you do with these, you guys, actually, with exponentials in particular, you can come up, there's not a unique equation that can model exponential growth. You could actually come up with a couple of different models that look different that actually describe the same trend, depending on how you want to do it. So here's one way, and then I'll show you a couple other ways. Do we know a sub 0 or the initial count? No. But what is this? What is this right here? After 2 hours, there was 400. So what is the 2 hours a measurement of? A measurement of time, and 400 is a measurement of A of t, or future amount. So we could say, just with this information here, that the future amount of 400 is equal to some unknown initial amount times e to the k. Now what was the time value? 2. And then we could do a similar thing with this information right here. After 6 hours, it was 25,600. So let's make another. So 25,600 is equal to the same initial count that we don't know times e to the k times 6. So, now what? Do you guys hear that? What two things don't we know in both of these equations? What two things don't we know? We don't know a sub 0 and we don't know k. But if we have two equations and two unknowns, this is something that we haven't talked about yet this year, but it is something that you've learned before. If you have two equations and two unknowns, what does that form? A system of equations that you can solve using either substitution, elimination. You've seen it like this before. Does this look familiar? Like 2x plus 3y is equal to 6, and then x plus 2y is equal to 2. Something. Remember doing something like this? This could be solved by elimination or substitution. The key is you have the same two variables that are unknown, but you have two equations to solve. And don't we have a similar type of thing here? I know they're exponential, but we have two unknowns and two equations. So we can set up a system of equations here. Elimination is not going to work here. We're going to have to do substitution. So what if I wanted to solve for this a sub 0 right here? What if you divide it by e to the k times 2? Then what we have is a sub 0 is equal to 400 over e to the k times 2. Now I know that's not an exact value because we still don't know k, but that's at least the value of a in terms of k. And now what can we do with this? Now we can plug that into here for that a sub 0. So now we have 25,600. Just make sure you're writing neatly so things that are supposed to be exponents are exponents and things that aren't are not. The value of a is 400, or sorry, a sub 0 is 400 over e to the k times 2, and that's multiplied by e to the k times 6. We actually don't have to. Almost. Do you guys notice that there are some things we could probably simplify here? And this is a property, another property of exponents that you guys learn and sometimes don't think about. But what if I gave you this to do? X to the 7th over x to the 5th. How would you simplify that? You'd subtract and get x squared, right? Well, don't we have something similar here? E to the k times 6 divided by e to the k times 2. Isn't that similar? What do we do then if they have the same base and you're dividing? What do we do with exponents? You subtract. This is not above your level, you guys. This is something that you absolutely can and should be expected to do. When you're dividing terms that have the same base, what do you do with exponents? Subtract. So how does that right side simplify? We have 25,600 still on the left side. How does it simplify? It's 400 times e to the k times 4. If you have k times 6 and you're subtracting k times 2, 6k minus 2k is 4k. Take a look at what's happened. You might not realize what's happened, but we went with an equation with two unknowns to what? An equation with one unknown. What is the unknown now that we're solving for? K. And once we find k, we can go back to here and find a sub 0. And then we have our model. So, how do we solve this for k? Divide by 400. Now, we're probably going to have to leave this as a fraction, because so the two zeros cancel, and we have 256 over 4. Now, that might divide evenly. Okay, so 256 over 4 is equal to e to the k times 4, but then 256 over 4 is 64. So 64 equals e. I'm sorry, I'm moving really fast here, to the k times 4. Now we do the natural log. Here, and we do the natural log there. We do the natural log everywhere. So now we have k times 4 is equal to the natural log of 64. And divide by 4. So k is equal to the natural log of 64 all over 4. Now we know k. That's awesome. We don't know a sub 0. So now we have to take this value, plug it back in there for that k.
Oh my gosh.
So we can find a sub 0. Come on, you guys. No, we can't stop.
Give up. Rebel.
A sub 0 is equal to 400 divided by e. And now that we know k, plug in your value of k. The value of k was the natural log. Make sure you write this as an exponent. Natural log of 64 over 4. And that whole thing was times by 2 originally. Almost. Almost. They will eventually. Now, do you guys remember that e raised to a natural log cancels? But only if we can get rid of this dividing by 4. This dividing by 4 is no good. Now, think of it this way. Instead of thinking about that whole thing being divided by 4, isn't that the same thing as having it multiplied by 1/4? Isn't dividing by 4 the same as timesing by 1/4? And instead of having a number in front of a logarithm, where can it go? Let me write this a little bit larger. This that we're looking at here is 1/4 times the natural log of 64. And that thing is times by 2. Okay, you're right. Yeah, before we start moving this number up, what about 2 times 1/4? Don't those simplify a little bit? So now we have 1/2 times the natural log of 64. And then somebody over there was mentioning what we could do with this 1/2. You put it back up as an exponent now. So now we have the natural log of 64 to the 1/2. So let's rewrite a sub 0. A sub 0 now is equal to 400 over e to the natural log of 64 to the 1/2. Well, no, the 64 is inside of the logarithm function. The 1/2 is just a... The 64 is not being... Say again. E to the natural log. So now this turns into a sub naught is equal to 400 over 64 to the 1/2. Which is 400 over 8, which is, oh boy, 400 over 8, 400 over 8, 50, there you go. So, look at that. Now we have a sub 0, and we have k. We are ready to finish our model. A of t is equal to 50. That's our initial count. Times e. What was our k value? Natural log of 64 over 4 times, we're not done yet, times t. Woo! Wow!
How many problems do we have tonight?
I can't remember how many. 9 problems. What? That's all?
No, I meant 16.
What problems were they?
3, 5.
Hold on. 3, 5, 13, 17, okay.
19.
Yeah, that was a good one.
29.
Okay.
31.
Ooh, okay.
35.
Whoa, okay. Okay.
Test on
Anyway, let's keep going. Let's do exponential.
my problems are weird.
Exponential decay. This is going to primarily deal with radioactive substances and isotopes. So, example 3. What's everybody's favorite radioactive isotope? Radium, there we go. That's exactly, and it's radium-221. That's the best asymptote, or isotope of radium. Radium-221 has a half-life. What? Has a half-life of 30 seconds.
It's actually 226.
Is it? Get out of here. You don't have that memorized.
No, I don't. I figured out it safely.
Do you really?
Well, in chemistry over with
Dude.
Well,
Legit.
That's that is the normal one. Yeah, the most stable one. That would be an isotope. The most stable one, that. It should make
I think he's right.
Anyway, radium-221 has a half-life of 30 seconds. If you go to Walmart and purchase a 10-gram sample of radium, no, if you have a 10-gram sample. Of 221, of radium 221. Find a model that describes the amount remaining at time t. Because just with the information given, we can give predictions based on increments of 30 seconds on how much remains. If you have 10 grams, after the first 30 seconds, there's 5 grams and so forth. But if they wanted just a random number like 48 seconds, you'd have to have a model so you can plug in that time value. It's the same thing. Same model we've been using. A of t is equal to the initial count, or the initial mass, times E to the k times t. The only difference here, since the base is just E, and that's a number larger than 1, what does k have to be to ensure that this substance decays and decreases over time? K is going to be negative. Okay? And that's not that we're going to have a negative sign, and you'll see what I mean here in a second. It's going to be built into the value of k that it's inherently negative. How do we do this? What do we know? We know that a sub 0 is 10. And after t equals 30, then a of t, or the future amount, or a of 30 rather, a of 30 is equal to what? 5. So we can plug this known information in. If a of t becomes 5 after 30 seconds, and we started with 10, that's e to the unknown relative growth factor times the time value of 30. So divide by 10. We get 1/2 is equal to e to the k times 30. This is the exact same as example 1, isn't it? Pretty much. Take a natural log on both sides. So the natural log of 1/2 is equal to k times 30. Divide by 30, and you get the value of k is equal to the natural log of 1/2 over 30. But didn't I just say that k had to be negative? Exactly. There aren't any negative signs, but Valerie, on your calculator, what's the natural log of 0.5?
Negative 0.69.
Yep. So the natural log of a fraction is already negative. So the negative sign is hidden right in here. So this value of k is negative. So we can plug that into our model and get a of t is equal to the initial count, 10, times e to the natural log of 1/2 over 30 times t. Now, if this were a class that you could use calculators, a follow-up question to this might be part B. How many or how much remains after 50 seconds? How would you answer that question? Now you plug in a 50 for t, but you'd have to solve that with a calculator. But you understand what you could now do with this model? Plug in any time value. Okay. So far, so good? Oh, God. All right, here's the thing, you guys. You ready? Are you listening carefully?
Yes.
Let me pause this.